Okie dokie. Let's see. Well, good morning, everyone. So this talk is really, I'm trying it out on you guys you folks a little bit. It's really about trying to understand what's going on in the industry and stepping back a little bit, because what we've had is a lot of, the steep knee of the Gartner hype curve, and I think a lot of us in the industry have gotten to the point where we wanted to step back and say, what is really going on here, and what are the real value propositions, and where are they? So that's what this talk's about. It's a little bit of an experiment. So I don't know, Dan, if people can ask questions in real time during when we're doing this, or if you want to collect them for the end or whatever. I'd like to have it as interactive as we can possibly make it over this. So whatever works, but feel free to ask a question anytime. So here's what I think I'm going to, and by the way, I have way too many slides for 30 minutes, but I wanted to have all of the information in this deck so you guys can have the context. So anyway, here's the agenda that I want to kind of pursue here. A little bit of a history of what the SDN, how SDN and all of this stuff came to be. What is OpenFlow? And what is even the OpenFlow SDN architecture? That haven't really been discussed very much. And then think a little bit about what architectures really are, and what ones do we know that scale, and what features do they have, and then where it's all going. And I'll summarize a little bit. I might have to jump ahead because through this, because again, 30 minutes probably won't be enough for this. But again, and stop me anytime you want. Ask a question. So. Oh, by the way, where I don't have a slide, I usually take the title of my slide and just jam it into Google Images and see what I get out. And so some of these images you'll probably recognize aren't mine. I got them from Google, unencumbered hopefully, but I got them from Google. So anyway, the point of this talk is that if I was giving this talk to, say, the ONF faithful, they might consider it to be controversial or provocative, and I hope you do too. And there might be a little bit of science in here, but if it's too much, we can skip that. So here's a lot of words, but the basic idea here was, in the early days of all of this, what people were saying is, oh, well, we're network architects, we're engineers, we're operators, and we're being presented with this challenge. And the challenge was, kind of concisely, oh, well, just provide state-of-the-art network infrastructure and evolving services at a fantastic rate, and do it cheaply. So basically, better, faster, and cheaper. Just do all of that. And, of course, that's a problem. And that's a problem today even, and it goes on. So the hypothesis that was really underlying all of this SDN stuff that was really, by the way, this is all germinating in Stanford and Berkeley and those sort of areas, with Nick McEwen, Martin Casado, who's now the CTO over at, or who was the CTO of Nicira, and now those guys are over at VMware. But so the underlying hypothesis here, oh, Scott Shanker was another one of the gang of three, keep that in mind. So the underlying hypothesis was that it was the inability to innovate in the underlying network. It was all IP, you couldn't do anything with that. Coupled with the lack of the proper abstractions resulted in this inability to keep pace with user requirements and keep TCO under control. That was really the hypothesis. And, there were several reasons for this. For example, requirements were all stated informally. I need some bandwidth over here. They're all out of band statically. Some of this stuff, we've known for a long time would be better done by machine. Obviously, we need programmatic automation of configuration management, monitoring, et cetera, if we want scale and efficiency. And so for the most part, all of this stuff is true. But the question that I want you to think about is whether or not do we need to change the overall architecture of the network in order to solve these problems. So hold on to that question. All right? That's sort of the crux of this. And these are questions that haven't been answered haven't even been asked in the community around us. We're all just marching in lockstep at OpenFlow SDN or whatever kind of SDN. So, given this hypothesis, what was really the problem? So it's like this, right? So this again, I think I typed enterprise network into Google Images, and this is one of the ones that came out. And I kind of like this one because the firewalls are actually on fire, so that's kind of cool. But the picture here is, okay, it's complicated. Why is it complicated? Well, it's because there's all of these there's no common way of thinking about a a forwarding plane in this picture. Okay, so a firewall has a forwarding plane, a switch, a router has a forwarding plane, an DS has a forwarding plane. All these things have forwarding planes, and they're all one-offs. So the consequence of that is that you have a box kind of oriented view. There's no network view of this. So, and excuse me, and it gets one step worse in that the actual policy that all of this stuff is in place to implement is actually really entangled with the configuration of the network. So for example, if you have a router and you want to implement some, or a switch, and you want to implement some policy on the edge, how do you do it? You generally have a bunch of ACLs, and the ACLs are the policy. They're both a statement of the policy and the implementation of it. So you have these three kind of things. No way to talk about a forwarding plane, kind of a myopic box-oriented view of the network, and then this entanglement of policy and configuration that's making this hard. And so that's the problem that the OpenFlow SDN people and the SDN people in general were attacking. This is another one, another piece of the same problem. So we work a lot in the IETF, and if you know the IETF, what we do over there is we make protocols, and we like to do that. But the result of that is you get protocol stacks, and that's not necessarily wrong or bad, but there are many protocols, many touch points, and there were few open interfaces or abstractions. So you had a handset that looks something like this in terms of its protocol stack. So this is causing fragility, and in the network, it's causing, and that fragility is actually a form of complexity, and we'll talk about that. That is costing, that's stopping people from hitting the TCO that they want to hit, and also being innovative in their networks. So, by the way, on the whole complexity, fragility, robustness thing, that's an entirely different topic. That is one of my favorite topics, and we can talk about that. I have a little bit about fragility in here because it's relevant. It's all relevant to fragility and robustness and complexity, but that gets us off on a different track. So if anybody wants to talk about that, just send me an email. We can talk about it. So how did we get here? I mean, why has this all happened? So the idea, and this is going back to the early days of SDN, was that anything networking was just too vertically integrated, tightly coupled, and not standardized. And it's sort of the same, that what people are saying is, this is like the mainframes, right? And again, and it kind of goes without saying that, this made the job of a network researcher pretty much impossible. And this was before the era of overlays, because nowadays it seems like the argument's a little bit weaker because you just throw an overlay over something and do whatever you want to, including, building commercial products. So that's a legitimate way of building virtualization. But the question is, and this is, so I'll have these questions in red, and I want you to keep these in mind. So does the OpenFlow SDN architecture, and I'll show a picture of that, map to the breaking down of vertical integration in the compute world? Because that was what was stated. I mean, we have to do, early in the history of this, we have to do to networking what happened in the compute world, okay? And so does it map? So let's look. I like this slide because this slide came from Martin Casado, who was, at the time, grad student of Nick McEwen at Stanford, and his other advisor, who was Scott Schenker. And they built, Martin, as part of his PhD program, thing, built this thing called SANE, which was Security Architecture for Network Environments, SANE. And, you can imagine what it is, right? It's a sort of a controller. It's a switch that was basically a TCAM that you could write access control lists into the edge under programmatic control. And it knew about hosts, routing, and topology, and it used OpenFlow to do this. Or it says in this picture OpenFlow 2.0, but that's a typo on Martin's slide. This is his picture. And so this was SANE. And then they built a version of this that was very Ethernet aware, and that was called Ethane. And then something called NOx, Network Operating System, came along that tried to integrate these things. And I just put insane on the top of it because they actually did have an insane, which was Internet sane. So this was sort of part of the genesis of all this stuff. So eventually what happened was there was a group of people who gathered in 104 Gates, which is a computer science building on the Stanford campus, every Tuesday afternoon. I wasn't there. This was before my time. And they kind of took Martin's work and what came out of that, and also some of the people who were already at Nicira at the time, And what came out of that was basically OpenFlow 1.0. And what OpenFlow 1.0 was is sort of just a little bit of formalization around ethane, right? So the idea here was you have an external controller. It somehow talked over a secure channel, although nobody ever used any. It wound up being just TCP, but the idea was it would be a secure channel to a switch, an OpenFlow switch, which was essentially a TCAM, and I'll show that a little bit more. And I'll just remember that the programming of this TCAM or the switch is done by by protocol messages called flow mods, flow modifications, and this is all done at runtime. So what could be in the flow table? Well, the flow table is a match action table. Sometimes you'll hear this called MAT or match action table, and the idea here is that it's a table in which there's a rule, and the rule matches on some part of the packet header. And in some cases, like DPI engines, it can go deeper, but in this case, it matches on the packet header. And then if there's a match, and we'll talk a little bit more about this, if there's a match, it can do some things, like forward the packet, encapsulate it, and send it to the controller, drop it, send it to the normal pipeline if there is one, or if that's well defined. That actually, number 4 there, actually never was really well defined. And then it has some, rudimentary statistical capabilities. So this was OpenFlow. This is what OpenFlow was, and the whole thing is being built on this. Now, again, I'm going to ask the question, is this the same thing as the breaking down of vertical integration in the compute world? And I'll show you some more pictures of this. Keep it in mind. So I got this slide from Rob Sherwood over at Big Switch, and this was from a talk that he gave, and he's trying to show here, oh yes, this is the same thing, because look, here's the x86 sort of, then there's some kind of virtualization layer, hypervisor, and then there's all these OSs and applications on top of this. And in networking, we're just doing exactly the same thing. This is the argument, okay? We're just doing this exactly the same thing. This is the argument. And what I want you to do is question whether or not this is really what's going on here. By the way, Dan, will you give me something like, you have 5 more minutes or something like that?
Sure.
Okay, thank you, because I'm not watching the time. So question whether or not this is really the case. Maybe it is, maybe it isn't. I'll have my opinion on that later. But this is core to all of this. So here's the classic OpenFlow SDN architectural picture from Nick McEwen. And you can see what it is. Basically, there's a bunch of simple packet forwarding hardware. This was core to it as well. There's kind of a CapEx component to this. So, all right, the switches are simple. They're basically TCAMs. They talk to the controller over a well-defined standardized protocol. There's a standardized, what was being called northbound NB API. This has kind of fallen apart in the meantime. And then there's a controller. Okay, now that's interesting. Well, we know, having lived through the internet era, we know that in order to have scale and resilience, you need a distributed system. There's some things you can do in a centralized fashion, like traffic engineering would work better if you could do it in a centralized way rather than something like, auto bandwidth or something like that. Because, if you think about it, it's a distributed system, and it has to hunt around for the new paths and everything, and that takes some time. If you had a global view of that, you might be able to do it immediately. But for scale and resilience in general purpose control planes, we know that you need distributed systems, right? Now, this is showing us, oh, well, there's a centralized controller here. Well, as soon as people started implementing this, they realized, oh, this has to be a distributed system for the reasons I just mentioned. So we got to this. Oh, well, yeah. Okay, see at the bottom here. I don't know if you can see this, but there's the salient features of this architecture. Separation of control and data planes, open interface to the data plane, that's OpenFlow, and some kind of logically centralized control. Because, again, the centralized single instance controller model is not going to scale or be resilient. Okay, so you need logically centralized control. Okay, so now let's ask the question. By the way, I ran this by James Hamilton, who's a cloud architect at Amazon, and he gave me this slide. Although I put the title on it. So what he wanted to see happen in the early days of this is, and what happened in the compute world was, it wasn't that the architecture of how you built a server changed. What changed was where the open interfaces were and where open source software was. So, for example, I don't know, in the 80s you would have bought, a VAX from DEC. And when you bought a VAX, you had closed hardware, you had a proprietary OS, and you had proprietary applications running on top of it. Nowadays, we all know we have x86, we have Linux, and we have open source. That's what happened to the mainframe business. Now, let's see. Is this the same in the world of compute, in the world of networking? I don't think so. That's why I say it doesn't look like it. I think the more, to be honest, I think that the closer analog would be to have an open source OS, network OS, and open source network applications, or even non-open source network applications that would run on a wide variety of switches and routers, even perhaps like white boxes. Now, a vendor probably doesn't want to say that, but that's the reality of it. The more precise analogy, or maybe an actual workable analogy, would be an open source network OS and applications that ran on white boxes. That would be more like what happened in compute. What happened with OpenFlow SDN is the architecture was changed. Here you can see the architecture wasn't changed. Oh, I wanted to say something about this logical centralization of the controller. I took this picture out of this really nice paper that was in Hot SDN last year in Helsinki. They made a key observation that if it's logically centralized, that just means it's distributed. So we have this word called logically centralized. It means distributed. Okay, once you have the thing being distributed, then you have a trade-off between how fast the control plane can converge and the state consistency model. We have that right now in the network, right? We use what we call eventual consistency to make the control plane converge faster, and that is above and beyond the sort of physical responsiveness lower bound, which is just the round trip between the switch and the controller, the packet processing time at the switch and the packet processing time in the controller. You can't go faster than that if you have to notify the controller to make the control plane respond. But there's also distribution of the state and the consistency that you're going to require of that state that's going to cause more delay. So, and there are other issues in here too, like, for example, I won't go into this, but let me just put this in your head. There's a breakdown. When you take the control plane off the switch, you lose the fate sharing between the control and data plane, and that means something to how fast and how you implement things, which also hasn't been analyzed in the industry. So this stuff isn't new, by the way. And here's a laundry list of things that I don't know if anybody remembers any of these things, but the idea of separating control and data planes is nothing new, and it's kind of a telco idea. The telco people like that, and you see SS7 and then AT&T and even Epsilon flow switching was an instance of this, although that was ATM. And people claim, oh yeah, this is just what happened in the TDM to voice thing, where you could say, oh, the SAS switch is a controller, or media gateway is like a switch, and H248 is sort of like OpenFlow. But I think this was more of in that case, I think it was really a second order effect. It was more about circuit to packet for voice. So if you back up and you go, okay, what is OpenFlow? It's this. I mentioned it was a match. The switch model is match action tables. So MAT, right? How many, how they're connected, what their attributes are, and they have these per flow counters I showed you. So it also has an application layer protocol, which is a binary wire format, the messages, the state machines, how you program this match action table switch. And it has to have a transport protocol. You got to get those bits to between the switch and the controller somehow. So altogether, while OpenFlow says nothing about how a target forwarding engine implements the abstract switch model, so it's an abstract, so OpenFlow itself is an abstract switch model. If we get time, I'll argue that it's built on the wrong set of abstractions. And it's kind of the reason why you're not seeing a lot of, widespread adoption of this technology. So here's this thing again, architecture and complexity. Let me show you this. I don't know if you're on the, I hope you're on the graph, the picture of the graph, but basically what winds up happening is, as you increase the number of protocols, configurations, and interactions, you get a curve, a robustness complexity curve that looks something like this. You need robustness, and here's where you're robust over here. I couldn't figure out how to just shade under the curve, so I gave up. That's what it should be shaded under. But so in these systems, you need complexity to achieve robustness. And I'll give you an example. I have a single interface that goes into a building, routed interface, and I don't, I go, well, that's not enough resilience, because what if the interface goes away? Then all the hosts inside the building are stranded, right? They don't have any connectivity. So here's what I'm going to do. And I don't want the host to carry routing. So what I'm going to do is I'm going to invent HSRP, and which is basically a way of, now I can put two interfaces in it, and the two router interfaces talk to one another, have heartbeat, and they switch their MAC addresses and so forth around, so that the host doesn't need to know there's two interfaces there, and it doesn't know that, it doesn't know any of this. So you still have a default route that points at the interface. And because they keep the MAC addresses alive, the host doesn't need to know about it. Okay, that's fine. Now I'm going to the right on this graph a little bit, because I've gotten some more resilience. I have resilience to I have robustness and resilience to the loss of an interface, but now I have more complexity, because now I've created fragility to the protocol that manages the HSRP, in fact, so that manages the MAC addresses and the IP addresses and all of that, and that's a new fragility that hadn't been there before. So I'll just tell you that these systems are called robust yet fragile. In other words, they have the property that if you increase the robustness somehow, you will create new fragilities. And that's always the case in these systems. And by the way, if you get over here on the left in the domain of the fragile, that's where you're looking for a new job, and things get bad over there. So you don't want that to happen. You can't really compute the place where you've got it optimized, but what it does say is that you can continue to create more and more complex networks, and eventually that will wind up causing the robustness of the network to decay. So there's no limit to how much complexity you can put into the network, but there is a limit to the amount of robustness. So can we characterize that? We can, but I'm not going to do it here. So I wanted to show you this too. So there's a lot of really nice work trying to understand, and this is all back to the OpenFlow model. There's a really nice body of work developing in the scientific community. This happens to come from systems biology, but the idea here is in biology or in life, which is just a giant network, among other things, there is this architectural feature which they were calling bow ties. And the idea here is that if you look at this picture on the left, there's chemistry and things over there, and all of that stuff gets formatted into a form, a rigid form, that all the rest of life and everything that happened in life on the right could depend on, basically. So the thing in the middle, which they're calling the knot, the red thing that says specialized, fragile, rigid, efficient, that's like a data formatting step. So in the case of biology, the canonical example is ATP metabolism, Krebs citric acid cycle. Every cell on the Earth uses ATP to transport energy, and it doesn't have to. It can depend on that. So life can build on top of that. Now, what does that have to do with us? Well, if you turn this thing on its side, it kind of looks familiar. This is the famous internet architecture hourglass. And so we see things in the internet world as horizontally layered. The bow tie sees it as vertically. I'm sorry, we see it vertically layered as in this picture, and the bow tie was horizontally layered. But the idea is that scalable architectures have this feature. Scalable, evolvable architectures have this feature. Okay, and the internet's an example, life on Earth is an example, the economy is an example, a lot of ecological systems have this. So this is a structure that you will find in something scalable. But if you look at where OpenFlow SDN is, well, it's kind of down here. So it's not exactly a thin waist or a knot the way people are trying to make it seem. But it hasn't been analyzed. So again, these are questions. Keep asking these questions. All right, let's skip this because I can see the clock. We're out of time. This is about RYF. So here's the key takeaways I want you guys to take away. So there's fundamental architectural building blocks of systems that scale and are evolvable, and that's what we want, obviously. They have this bow tie hourglass thing I just told you with RYF complexity. We didn't get a chance to talk about that. Um, they're massively distributed. Okay, BGP, your immune system, robust control loops, TCP, that's a robust control loop in that control theory sense. I can explain that if somebody wants to ask a question about that. They're highly layered, right? We have layering. We saw that. The immune system, energy metabolism, very layered. In the network, very layered. Protocol-based architecture. We use protocols to communicate with the external world. You know, TCP, BGP, OSP, you know, all of this stuff. Biology has something called degeneracy that we haven't really quite gotten to yet. Degeneracy just means that the elements can do parts of other jobs, and you can build, we build redundancy, n by n, 1 by n or whatever, which is can be built out of degeneracy, but degeneracy is something we'd want to get to if we can ever do it, because it gives us evolvability. By the way, if you look at this picture, this tells you exactly why IPv6 is hard to deploy, because it's trying to change the narrow waist or the knot. But if you look at OpenFlow SDN, okay, it's first off centralized. It doesn't really form a bow tie or an hourglass. It's delayered, right? You know, if you think about it, the match in the TCAM can match over all the header fields, or as many as the hardware will do, which essentially delayers the network. Because inside the OpenFlow network, there's no protocol stack. It's all flat. It's protocol agnostic, which sounds good, but in a way, it's not good. And it's not degenerate. And in fact, if you think about things like network function virtualization, which is a standards activity that was spun up by 20 of the carriers over in Etsy, it's actually further specializing components, which really causes the network to become more brittle and harder to evolve. So, are we out of time?
Well, David, you can actually take some more time if you need it. We have a total of an hour. David, you can take more time if you need it. We have a total of an hour. We'll just cut away from the question and answer time.
Okay. All right. So let me just review what this OpenFlow is and kind of frame up the questions I've been asking in summary. So here's the OpenFlow version 1 model, right? So basically, remember, a packet could come to the switch, which is a TCAM flow table. If it finds a rule, it applies the action to forge the thing. And then by configuration, it can either drop the packet or send it to the controller if there's no rule. So this is nice. Everybody understands that. The problem is it was too simple. It didn't have feature functionality. For example, it couldn't increment or decrement the L3 TTL, so it couldn't do anything with L3. And its expressiveness was suspect. There are things you can't actually say, and I'll mention a little bit about that. And the abstractions themselves, I'm calling them lossy, and I'll tell you why. So this was a problem, and there was another problem here, which is that these TCAMs are the most expensive, hottest, least performant parts of the forwarding plane, and as a result, they're small. You know, so the typical TCAM entry when this was all starting was, a couple thousand entries. Well, if you look at the internet, just in case of routes, there's almost 500,000 routes out there right now. So you're not going to build that TCAM with 500,000 entries in the near term, and if you do, it's expensive. So what had happened was people went, oh, this is a problem, because when you try to put too many rules, or if you try to look at the cross product of routes and policies, which you do, that explodes and you don't have enough TCAM space. So now you have to build a controller that basically has a cache management like LRU, style scheduler for the rules, and this is it's a real problem. So this was nice, but it was too simple, and it was TCAM, and the TCAM model was difficult. So now today we have this, and this is the switch model. And so the idea here is you can flatten out the cross product of routes times policies into these many tables. And the way this worked was, or is supposed to work, is when a packet comes to the table 0, if the switch is programmed with actions already, what you do is you accumulate those actions in what's called an action set, and then at the end you execute them. So in this way, every table sees the original switch, the original packet. Because, of course, if it didn't see the original packet, you'd have no way of knowing what had happened to the packet before it got to you, so you wouldn't be able to formulate a rule to operate on it because you just don't know what's to the left of you for n less than whatever your n is at your table index. So this was that, and people went, okay, well, that's interesting. Well, that's really not implementable on ASIC hardware. You can do it in software. Realize you can do anything in software. Doesn't make it right or efficient or anything like that. So by software, I mean real software, open virtual switch, or I mean, NPU, microcoded or flow processor. Those are all really software. The ones that are hard are ASICs, right? And that's where, and the ASICs are the sort of workhorses of the forwarding plane. So this thing is not implementable on ASIC hardware, really. And if you start looking at it, so I mentioned why this design, it's trying to deal with this combinatoric explosion of route times policies in a single table. But it's not tractable. I mean, if you just look at this from the simplest, I don't know how many people remember their discrete math from high school or college, but basically, how many ways to choose the first table if there's n tables? Well, there's n. How many ways to choose the next one? Well, n minus 1. How many, So eventually, there's n factorial tables, combinations of tables. And there's 256 possible tables because there's 8 bits to describe a table. So 256 factorial is kind of a big number. And now, if you want to really start trying to compute this, because that's interesting, but what are the actual constants in here? Well, if you look at what you can do in in the match field of table, okay, imagine that there's L bits of match field, and these include, all the header information, and say that's L bits wide, right? Well, okay, now there's 2 to the L possibilities of that. But for each of those 2 to the L possibilities, there's some number of actions. So now you're starting to have a constant that's starting to look like 2 to the L as an exponent of the number of actions you have, plus a bunch of other stuff that I couldn't figure out, like, table sizes are different, there's metadata, there's group tables. I mean, it's very complicated. So you're not going to see this implemented in hardware this way anyway. So at the end of it, this thing is too complex and too brittle. And I just showed you the algorithmic complexity, but what is a flow in this? You don't know what a flow is, right? Because in the other table, it was pretty easy to know what a flow is. It was the thing that matched on the TCAM. But now here, you're matching across several tables with several different kinds of actions. You don't know. So it's not naturally implementable on ASIC hardware. I mentioned that. There are all kinds of, we didn't talk about this, but there are all kinds of really interesting network reasoning systems and network compilers that were built on OpenFlow 1.0 because they knew what a flow was. They could concisely characterize what a flow was because there was only one table. But this breaks all of those. None of the lossy abstractions were really fixed, and I'll talk a little bit more about this, and all of these architectural questions I'm asking. So let's go back and ask a question. Is the flow-based abstraction right for general purpose network programmability for some value of right? More questions than answers. So what is this lossy abstraction thing? Well, the problem here is current versions of OpenFlow, including 1.3 plus whatever it is, 1.3.1 or whatever we're on, they do not work well on ASIC targets. And as I said, ASICs are the workhorses of the forwarding plane. And the basic thing here is at the end of the day, the answer is setting a forwarding table entry just loses too much information about what the application or controller writer's intent was and makes it difficult or impossible to leverage switch hardware features, right? And I'll just talk about 2 of these. I mean, here's the laundry list, but I'll talk about the information loss and the leakage one just informally here. So information loss, suppose I'm an application and a controller writer, and the application says send this L3 packet, to somewhere. Here's the source and destination, L3 packet, just like we do today. The controller can't tell the switch that the packet's an L3 packet. It doesn't know. There's no way to talk about that. So that information gets lost between the controller and the switch. On the other hand, going the other direction, information has to be leaked in order to use hardware. So let me give you an example. There's millions of such examples, but here's an easy one. So in a typical ASIC, you want to do MAC learning and MAC bridging, right? I mean, that's 2 kind of fundamental things. But because of the way ASICs are designed, you have to optimize the surface area, because that's the most expensive thing when you're building an ASIC is, you have to map the surface area into functionality that, for the vendor is going to generate revenue, really. That's the answer. But you have to, there's all kinds of design rules that are like that. So when you build a learning and forwarding layer 2 switch, what you do is you make one table that has 4 keys. For learning, the key is the source port and the source MAC address. For forwarding, it's the desk port and the desk MAC address. Okay, how would you do this in OpenFlow? There's no way to do it, because OpenFlow doesn't have a way of talking about shared tables. So really what would have to happen is there would have to be what's called a HAL, a hardware abstraction layer on the switch that somehow could receive the flow mods. Remember, that's how we program the switch, and kind of decompile the intent of the controller writer. Now, obviously, that's not going to happen because that's just not doable, right? So in that case, you'd have to leak information. The controller writer would have to sit there and with the manual for the ASIC, and as a result, the controller is going to wind up, including platform-specific code, which it does today, which they all do today, and that just means it's brittle and not portable, and it just specifies too much of how and not what the switch should be doing. So this is a information theoretic problem with the whole thing right now. I think I'll just leave these for you. These are pictures of where these kinds of abstractions go, and I'll get rid of this. I'll not do this. So I'll just say one thing about this. The Google guys came along and proposed a solution to all of these, but it was seen as too futuristic and too dynamic by the OpenFlow Technical Advisory Group, Open Networking Foundation. So a dumbed-down version was proposed. I was kind of involved a little bit in this, and basically it was less dynamic and with no runtime component really, and a small set of predefined models, and that was still seen to be too ambitious. So right now, in order to attack this, the current ONF direction is to add what they're calling table typing to OpenFlow version 1.3 or later. And there's a working group called the Forwarding Abstractions Working Group that's working on this. But this is all converging on something called forces that's in the IETF. So you kind of have to ask yourself, why isn't this forces and why hasn't forces succeeded? Those are open questions. So it was a great idea, but wasn't really executed against. So a quick summary of all of this whirlwind tour of this. OpenFlow 1.0 is widely implemented. Widely is a relative term, but it can be implemented on current ASIC hardware. You just use the ACL TCAM for this. And there's a few software implementations of 1.3. 1.1 is not widely implemented in hardware for the reasons I mentioned. I think the table typing thing could be part of the solution, but I'm concerned because the complexity is growing at a really, really astounding rate. And then there's all these questions of architectural, the architecture, the scalability, the resilience, all of this stuff. So there's other things too going on, like what I'm calling the SDN continuum, and this, I'll end it with this, but look at this. This is the future, which is now. So forget about all this stuff above the red line. I was just saying there's controllers, there's orchestrators, there's applications, there's service layers, there's all kinds of interesting things going on down there. But at the SDN level down below that, there's kind of 3 points in a continuum in a space that you can kind of pick out and kind of try to analyze. And I'll call the first one data plane SDN. And this is the OpenFlow SDN model, but there are other things that you could use for the OpenFlow piece of it, like forces. So here you get complete separation of the control plane and the data plane, open and programmable interfaces to the data plane. And initially the idea was applications are smart, they'll program the network, but people have really backed off on that because that's not a scalable thing. And then if you move to the right a little bit, you can have this sort of this control plane SDN idea where you retain the existing distributed control planes we have today, but you make it programmability. You make the control plane programmable. So you get network-aware applications. So you can learn things about the network, and you can maybe have the application modify its behavior or or ask for certain kinds of resources from the network. So examples of these are PCE, I2RS, the various vendor SDKs, things going on over in the IETF, and proprietary SDKs. And then if you move all the way to the other side, you have this kind of overlay SDN. And here, what you do is you retain a simplified control plane. So, you have ISIS or something like that running in the network. And then you overlay, and you don't care about what the controller data plane underneath you is. You just say, give me 32, 64, 128 wide ECMP on 10 or 100 gig, and I'll put another control plane over the top of that. And use various overlays technologies, NVGRE, STT, VXLAN, whatever, Lisp, whatever. And this is the VMware and the Sierra thing. So here you don't care about what's underneath you. So there's kind of a continuum, and all of these things are playing at the same time. And this space is being explored by the industry right now. So that's kind of a whirlwind tour of all of this. And I think that's my last slide, and then we can do some Q&A if people have questions. Yeah. Okay.
Thank you, David. Very interesting presentation. This seems like an excellent time to take questions. You can raise your hand, and I will unmute your phone, and you can ask your question verbally, or you can type it into the question dialog box. Are there any questions?
Too much.
All right. Here's one question coming in. If SDN is not a bow tie shape, is SDN scalable?
Yeah, that's a good question. Thank you for asking that. Who asked that, by the way? You get 2 points.
Okay, that's actually me.
Oh, you asked it. 2 points to you. That's a good question. Somebody asked me that before, and SDN itself is really not an architecture. It's kind of a a bunch of facilities and things you can do. If you start saying something like OpenFlow SDN, that's why I tried to frame it up that way. That is an architecture, and doesn't have this. And this is what I was trying to point out. It doesn't have these properties. So personally, and time will tell, right? Things evolve and change. But right now, if somebody was to ask me, does this look like this is going to scale, like to internet scale, or to hyperscale data center scale? I would have to say it doesn't look like it. But again, in time will tell. But if you go and say and if you kind of get into the systems theory realm, you find out that these things at scale do have these shapes and do have these features and if you build something that doesn't have that, you kind of have to ask yourself, I wonder. And again, these questions haven't been asked. So.
All right. Next question had
the answer to your question is it doesn't seem to me, from where I sit, that this is going to form the basis of something that will be as successful as the internet has been.
Next question has to do with network function virtualization. He said it is more specialized. Why does it have to be so? Couldn't software-based networking elements be based on the same open standards that hardware products are using? Maybe I'm misunderstanding.
No, it doesn't have to be. But the way it's going right now is people are asking, can I build a special purpose software appliance that does something like X, some X. So I want to do service chaining. So what I have to do is I have to send a flow through a NAT, an IDS, a firewall. And so what I'm going to do is I'm going to chain these things up, and what I'm going to do is make them all x86 boxes. Now, if you go back and say, I'll put it all in one box, then you're starting to do the vertical integration that these guys are trying to break down. So there's perhaps a sweet spot between the vertical and the horizontal, but in general, specialization causes brittleness. It's like I'm really specialized. I have a 10-ton skull, but if an asteroid hits, a mouse is going to win because it's less specialized. So it's an issue of how these architectures are able to evolve, how they're able to deal with their whatever threat analysis they're presented with, and how they scale. And that's what I was alluding to.
Okay, are there any more questions? I don't see any more hands raised. Going once, going twice. Well, with that, I think it's time to conclude today's presentation. David, do you have any last thoughts you want to share?
Only that if people have questions on all this, because there's a lot of stuff in here, you're more than welcome to have the slides or contact me directly and send me an email or whatever. Glad to chat about it.
Well, thank you, David. It was a very interesting presentation. I learned a lot from it. To everyone, thank you for joining us today. This is the last in this series of Viata webinars. We'll be starting up another series of webinars in June, and I promise that we'll contact each and every one of you to let you know when these start. Do come back to viata.com and check our Learn page to find out when additional ones will be posted. I'll be putting something up there in a few weeks listing the next webinar schedule. If you do have additional questions, you can contact me, Dan, at viata.com, or you can contact sales at viata.com if you have any product questions. Thank you for joining us today. You will be receiving a link with a recording of this webinar if you have any, if you want to watch it a second time, and I hope you do. Thank you for joining us today, and I think it's time to close this webinar.